Hey guys, I'm Pat Kelly. Okay, in this problem, they give us a differential equation, but the directions are to use a power series to solve this differential equation. Okay, so it takes a little bit of work, but let's do it. The way you want to get started is you're anticipating your answer is going to be a power series. So what I would do is start by letting our y equal, and what you do is try to write down the most generic power series that you can, and we're going to try to fill in the specifics. That'll be our final answer. But the most generic power series that I can come up with is the summation from n equals 0 to infinity of some kind of coefficient, a sub n, multiplied by x raised to the n. Okay, and we've got to try to be more specific than that. The way that I'll do that, the way I'll be more specific, is if I do have a y equals, I can try to get a handle on what y prime equals. So now you're doing a derivative here of actually just a power, so good old power rule. What you have to imagine is the n comes in front, multiplies by that a sub n, the coefficient, and then the x drops down a power. The reason I left my sigma blank for a second is realize that that actually is going to start with an index of 1, all right, because that x to the 0 power above would be a constant, and that differentiates to 0, so it's not represented here. Okay, so that's a good start. What it actually does is gives us some building blocks that we can now use to plug in to the original differential equation. So I'm going to take these two expressions and put them into here. Slide over for some more space. So my y prime is all of this. So I'm going to write down the sum n equals 1 to infinity n times a sub n x raised to the n minus 1. Okay. But then when I go to put my y in right here, I'm actually going to do a little bit of multiplication in my head. The 3 is easy, plus summation, and I know y is going to end up going from n equals 0 to infinity from here. I have the 3 that I mentioned. You still have your a sub n, but the multiplication that I mentioned was that we do have a factor of x here. Let's multiply that by this x here inside of our summation. So we're just going to have x raised to the n plus 1 power, right? Add exponents. Okay, that's good. And that all should equal 0 from our original equation. All right. That's like a substitution step and a little bit of multiplication that we did in our head. But it's the next step that can be a little bit, I don't want to say tricky, but it might not be glaringly obvious at first. Let me try to explain what I do. Is in my next step, I want to try to get the two different x's to have the same power so that I'll be able to do that balancing act that we've actually done many times where we make the coefficients match on either side of the equal sign. You can really only do that if you have the same powers of x on either side of the equal sign. So I'm going to try to get this x to have the same exponent as that x. You can see what that means here in this case is that the exponent here needs to bump up by 2. Okay? So the way I do that is with this summation, if I want that power of x to bump up by 2, I actually start the summation 2 values of the index earlier. So this is going to be n equals a minus 1 to infinity. By starting 2 steps earlier, it's going to make this n value 2 higher. Okay, so instead of n minus 1, it'll be n plus 1. And I also have to take that into account anywhere else that I see an n. This n bumps up by 2. This n in your subscript bumps up by 2. And this n bumps up by 2. That's what we were shooting for. We wanted that to be n plus 1 in the exponent. Okay, good. So a little bit, like I said, not tricky, but make sure you catch what we did. And if it helps, make sure you think of why we did it. We wanted those two x's to have the same power. We do that because of that balancing act that I mentioned. And I even mentioned a couple times already that you have the other side of the equal sign. So in this step, let me throw this term, this whole term here, onto the other side of the equal sign. So it's just going to be a minus 3 over there. So I'll write that as my summation, n equals 0 to infinity minus 3a sub n x raised to the n plus 1. I'm going to put parentheses there just because of that minus sign. Everything in there is inside of the summation. Okay, so I'm about ready to do my balancing act, but in fact, before I even do that, imagine if you did plug in a minus 1 for n on the left-hand side. A minus 1 for n, that's going to be a minus 1 plus 2, that's a positive 1. A sub 1, do you see it? That's going to be 1 times a sub 1, x raised to the 0 power. All right, x to the 0 power. The reason that's important is on the other side, you're starting at an n of 0. So as soon as you put a 0 in right there, you're already at an x to the 1 power. So you'll never have an x to the 0 power. And what that tells me over here then is that when n does equal a negative 1, you're going to have 1 times a sub 1. Remember, we said that that's what we'd have. But it doesn't have anything to balance with on the right side of the equation, so a sub 1 equals 0. Okay? A little bit tricky again. From there, then, we will have matches on either side of the equation. So let's try to express that in terms of our a sub n plus 2. Now what I'm trying to do is to get that balance, I'm going to try to look at a sub n plus 2, and all of these x raised to the powers will match, they'll be the same. So I'll take this a sub n plus 2 and solve for it, which really just means divide over the n plus 2 as the coefficient here. Okay? So what I have here as my coefficient of x to whatever power is going to be a minus 3a sub n. I tried to write that up a little bit because that'll be a numerator. My denominator will be that n plus 2 that I divide over. So n plus 2. That's all from that balancing act. And what it does for me is gives me a little bit of a formula for a sub n plus 2. Okay? Whenever I want any a sub whatever, it's just going to be the 2 values of a before it, okay? And then also multiplied by this 3 over n plus 2. I'll show you what I mean, because we actually need to find those a sub whatevers. So let me slip into another color and slide over here. And now what I'll do is get a bit of a list of all my different a's. And I'll start with a sub 0. And this will look redundant, but a sub 0 is just going to equal a sub 0. I don't know what it is, but it equals itself. And then a sub 1, we did get a value for. That was 0. Comma, a sub 2, and now what I do is I start to use my formula. So we're looking for a sub 2, which means that n is like a 0. So minus 3 over 0 plus 2, that's going to be a minus 3 halves times the a sub n. My n is 0, so a sub 0. And what you're doing, you've seen this before with sequences and series, right? You're ending up with some recursion as you get a sub 2 in terms of a sub 0. And you'll see me do that quite a bit more here with the rest of my list. What I want to keep doing is listing the different a sub whatevers. Why? Not tedium, not because I'm trying to give you busy work, but because I need to start looking for a pattern. Remember that from sequences and series as well? We need to try to find a pattern so we can generalize what a sub n looks like. All right. A sub 3, follow your formula. N would be 1. Notice right away, a sub 1, but that's 0. So the whole thing blanks out to 0 for a sub 3. That was nice. Comma, a sub 4. Let me try to get a handle on that. A sub 4, following the formula, my n is 2. So I'm going to end up with minus 3 over 4 times a sub 2. But I have an expression for a sub 2 right here. So I have minus 3/4 from here. And my a sub 2, I replace with this expression involving a sub 0, minus 3 halves, and then a sub 0. And if I could squeeze this in, I'm going to rewrite that, because these two different minus 3's, I'm going to group together and square it and divide by, here's a 4 and here's a 2. I'm going to write that as 2 squared times 2. Of course, you still have times a sub 0. Now, right away, you might say to me, well, come on, you can do this. Negative 3 squared is 9. Why don't you write that? And why don't you just make this 8 on the bottom? And the answer to those questions is that I'm looking for a pattern. So you'll see this. I'm already thinking ahead what I'm going to have down here. You're going to look for a pattern in your other a sub whatevers. Where am I? That was a sub 4. So I want to pick up with a sub 5. A sub 5 is going to bank on a sub 3, which is 0. So that's good again. A sub 6. So that's going to be minus 3 over 6 times a sub 4. And I know what that is right here. That's the minus 3 squared times 2 squared times 2 times a sub 0. Let's see if I can rewrite that. Again, looking for a pattern. I'm definitely seeing a negative 3 raised to an incrementing power. First it was 1, then it was 2, now it's 3. And down below, I'm going to write that as 2 raised to the 3 power, because I have 3 factors of 2. And the 6, I'm going to write as 3 multiplied by 2. Why? Well, again, I have a method to my madness. I'm looking for a pattern. And times a sub 0, comma. That was a sub 6. I'm just going to do 2 more. I've got to see the pattern. A sub 7 is 0 again. A sub 8 equals minus 3 over 8 times this a sub 6, which is minus 3 multiplied, raised to the 3 power, divided by that 2 raised to the 3 power, 3 times 2. I got some parentheses going here. All that's times a sub 0. Let's see if I can rewrite that. I think I have room right here. This equals, again, I'm trying to rewrite to see a pattern, and I like the minus 3 raised to the power that keeps going up by 1. And the 2 down below, I like that continuing to go up to the same power, which is nice. So what would be left over here? 8 times 3. I'm again not going to do that multiplication. I'm going to try to rewrite that as actually this time 4 times 3 times 2. That would be 8 times 3, right? But see, what I'm now finding is the pattern of minus 3 raised to a 4, 2 raised to the 4, and that's actually shaping up to be a factorial. Whew, huge sigh of relief. Now I'll come over here and try to write what's actually my final answer, okay? So y equals, and what I have is my most generic expression of a sub n. Notice they all depend on a sub 0. So I think I might bring that all the way outside of my summation. And n equals 0 to infinity. And then that pattern that I was looking for is going to be minus 3 raised to the n divided by 2 raised to the n times n factorial. And that's great. That's all just the coefficient. Don't forget to multiply it by x. And most of the time, that x is going to be raised to just the n power. But remember how all the odds blanked out? A sub 1, a sub 3, a sub 5 all blanked out. So we're actually looking for just the even powers of x. So I'm going to write that as 2n. And that'd be my answer. Okay? Give yourself a pat on the back for that one. Practice some more on your own. Okay?